Now, we are going to show you some of the simple examples of how statistical calculations help us understand how entropy plays an important role using very simple examples. So, estimating entropy for various processes, and this part is taken mostly from Kendall's book of molecular driving force. So, first we will discuss about free expansion of gas. Remember, in our description of classical thermodynamics, we already mentioned that we already showed that how expansion of gases into full volume will give rise to entropy. Remember our discussion that the work done for free expansion is 0, and if it is an insulated system, then heat change also will be 0, and therefore, internal energy change at least for ideal particle will be 0. And then we said that since it is an irreversible process, we have to create a reversible path, and if we do that, then there will be a Q reversible which is non-zero, which will give rise to an increased entropy. Also, intuitively you can understand that the particles which were confined to only one part of the box now have more and larger space to move around, and therefore, of course, it should have higher entropy because it has more number of options. These examples use very simple model, is called lattice model, which lattice models are models where particles occupy a particular space in a lattice points. For example, a solid, you know that in a solid sodium chloride occupy a particular lattice points, and they do not move away from those lattice points, they only vibrate around those lattice points. Unlike liquids and gases which translate, solid particles cannot translate, but rather they vibrate along its own equilibrium point. However, they can have different configurations, they can attain different configurations based on based on its allowed positions. It cannot occupy all possible positions, but it can occupy only lattice points. For example, in a one dimensional lattice, it can occupy 0, 1, 2, 3, these are the positions, whereas for non lattice systems we call off lattice system, their particles can occupy any positions. So, idea is that using lattice points we make our life simpler for doing the calculation. So, it is not exactly a model of free expansion. We have done that, we have shown that using simulations, an exact one almost. However, here we are using for calculation purposes very simplistic model where the lattices are fixed, like they are like a box. So, the particle can occupy either this point or this point or this point in the lattice, and there are let us say 3 particles, and each particle, and they are indistinguishable particles, and each particle can occupy only one lattice points, not more than one particle can occupy lattice point. So, whenever you have the situation, so remember we discussed that whenever we have indistinguishable particles, but distinguishable cells, then it should have the star bar kind of problems, right, that it will follow the star bar statistics. But only difference with this particular thing is that in that case one box could have contained multiple particles. Here the situation is slightly different. Here only one particle can occupy one lattice points. It can be free or one, not even two. So, here essentially what we are choosing is that how many ways I can choose the 3 particle for the 3 boxes. So, basically I am choosing the box, and since they are indistinguishable, it does not matter. If the particles are distinguishable, then I could have taken any one of the particles. So, that means 3. Then for the second lattice point I could have taken in any two different ways, that would be 2, and then for the third particle that is only one possibility, that would have given us 3 factorial ways. But you know that 3 factorial is nothing but permutation, but you know that when it is indistinguishable, when you are grouping them together, I have to divide by 3 factorial as well. So, it becomes 3 factorial by 3 factorial, which is nothing but 3C3. So, how many groupings of 3 I can do out of 3 particle, and that is 3C3, and we know that is only one possible way. Visually also you can see that there is no other way I can put 3 particle in 3 different boxes. Okay. So, here essentially we are choosing the boxes, and there is only one way of doing that. So, there is a very tight lattice, there is no extra space available to it. Now, let us say I am talking about free expansion. What is free expansion? There is no work done, particles are free, it just has more possibility to go, there is no energy advantage, no reason for it to go based on energy alone, but there is just more availability, and that is the situation given here. I have 3 particles now, but I have 4 lattice points. So, that means I can choose that which of the 3 boxes or lattice points will be filled by these 3 particles, which of the 3 out of how many? 4. Which of the 3 out of these 4 will be filled? And that is nothing but a combination problem of 4C3. 3 I have to fill up and I have 4 situations. I can put any 3 out of these 4, any 3. So, if I number them, and the boxes are distinguishable, I told you, if I number them as 1, 2, 3 and 4, I can choose 1, 2, 3, 2, 3, 4, I can choose 1, 3, 4 and I can choose 1, 2, 4. There are only 4 possible ways, and that is 4C3. So, now, why we say it is free expansion? It is free expansion because it does not have to do any work. Whenever there is external pressure is 0, it is called free expansion. If there is no pressure, nothing is prohibiting the particle to go to the other lattice points, and therefore, it is free points. And why? And we see that the W has changed from 1 to 4. It is just the possibility. Remember, we discussed that entropy is nothing but possibility. Wherever there is more possibility, there is more entropy. Here exactly that example is given here. More possibility is leading to more W, leading to more W means microstates, leading to more entropy. Now, increase it a little bit further. I have now 5 spaces and I have only 3 particles to fill up. More spaces, more than it was before. Now, I have to choose which of these 5 will be filled by these 3. So, it should be 5C3, and there are 10 possibilities. So, you see, as the number of lattice points increasing compared to the number of particles, it is entropy is, or W and entropy is both are increasing, like W is increasing and therefore, entropy is increasing. Exactly that happens for free expansion case, right. Whenever there is a particle here, it has only this much space to occupy, and then suddenly I have opened a new chamber for the particle to move in, just because it has more space to go, just because there is no restriction for it to go. Unless we restrict it, that is a different situation. I force the particle not to go, that is a different situation. I am forcing the entropy to not increase, and that is work against the entropy. Entropy is possibility, but if you reduce that, of course, you are reducing the possibilities by force. But remember again one more thing, that one cannot reduce, one cannot work being a part of the system. For example, we can clean up a room and reduce the entropy of the room, but being a part of the environment, being a part of the universe, we cannot really reduce the entropy of the universe, because that we are just part of that. By cleaning up the room, we essentially have done some work, created heat which is dissipated to the environment, and eventually we have increased the entropy of the universe. However, we have decreased the entropy of the room. So, that is a little bit of a digression, just to tell you that although we can do work to reduce the entropy of a particular subsystem, the overall system which is isolated for a spontaneous process will always increase entropy. Okay. So, now this we have seen that by very simple lattice model we can actually explain that a free expansion will increase the entropy of the system. Now, let us go to the next example, mixing of gases. So, we have seen that for mixing of gases entropy increases, and we have seen that mixing of gases entropy increase is part due to the volume increase itself, right, because it was initially one part was occupied by, let us say, red particle, another part was occupied by blue particle, and then we saw that when we joined them together, then blue particle went all over the 2 boxes, red particle went all over the 2 boxes. Now, we have a mixed system, the volume is now double, which means that for blue particle also entropy has increased, for red particle also entropy has increased. But what if the situation is different? What if we have the same box, but only the particle have mixed? Now, we can do both the situations. Now, let us take a box, left box, where there are 4 boxes and 4 particles. We know, looking at the figure itself, that there is only 4C4 ways of doing it, because there are 4 boxes I need to fill with 4 particles and only 1 particle in a box. So, it is 4C4, and in this case there are red particles, again 4C4. So, how many possible ways we can do that? We can do that in 4C4 multiplied by 4C4. And why we are multiplying it? Remember, and probability multiplies, which means that I have to fill up left box with 4 particles and right box with 4 particles. I do not have an or choice. I may not choose not to fill, I have to fill it. So, I have an n probability, or rather number of possibilities to calculate. Remember, it is when you calculate the probability, it is a numerator by denominator. Here we are talking about just the denominator or number of sample spaces, and whenever there are 2 sample spaces, they will multiply. For example, remember how many possibilities is there for throwing a dice? 6 possibilities. How many possibilities are there for throwing 2 die? 36 possibilities. If you pair them 1 6, 2 6, 3 6, 4 6, 5 6, 6 6, then 2 6, 2 1, 3 1, 4 1, 5 1, 6 1, like that you will have 36 possibilities. So, always the number of microstates will multiply, number of sample space for 2 different samples will multiply, and that is the reason also that it is multiplying. Now, this is purely unmixed and unmixed 2 systems. Here we are not mixing it, we are taking a mixed situation in this case. So, the left box now has a mixed situation where I have a mixture of particles. Right box also have a mixture of particles, and I have to fill up 3 boxes out of the 4 with black, then automatically my red will be filled. So, foresee 3 ways of doing so, and right hand side also foresee 3 of doing so. Then total possibilities will be 4 into 4 or 16. Now, instead of 1 red particle, let us mix it even more, let us mix it equally. Still I know boxes are not mixed yet, okay, only the particles are mixing only. So, that means the volume is remaining constant, but instead of 1 type of particle I have 2 types of particle, and there also you see now I have to fill up only 2 out of 4 boxes, then automatically the other 2 will be decided. So, it will be 4C2 multiplied by 4C2, and I get 36 possibilities. So, as you can see, from unmixed situation to a mixed situation, the entropy increases, and this increases just because of mixing of gases for a fixed volume. But remember the other situations where I have a one box of one particle, another box another particle, and join them together, the volume becomes double. Here the number of lattice points will become double. So, instead of 4 it will become 8, and the number of particles also will become double. Instead of 4 it will be 8, and I have only 2 types of particles, and that is the situation that is here. Now, I have 8 lattice points, and I have to choose 4 for red and 4 for black. So, how do I choose that? So, I have to choose 4 out of 8. So, 8C4 for the black, and then automatically the rest will be chosen. I do not have to really choose for that. So, let us do only 8C4, and what we observe that it is now 70. So, here not only there is a mixing, but also the volume also has increased, and because of these 2 effects, that entropy is even more than a fully mixed systems, and that is where shows that whenever there is a mixing will occur, then entropy also will increase. So, let us see another situations. Remember the balloon demo that we did, where we put the balloon and stretched it, and we left it, then it shrunk and the fingertip became cooler. So, what happens in that case? So, when you leave the balloon to on a table, it is in its equilibrium state, and it is not very long, not very short, it is some intermediate situation. When you stretch it, lengthen it, you are actually working against entropy. Why? Because it is not the energy that holds the rubber, it is a polymer that holds the polymer together. I will show you in a moment that it is the entropy that makes it smaller. If you stretch it, you are actually working against entropy. Then when you release it, then it spontaneously releases and increases the entropy, and that will actually take the heat out of your fingertip, making it cooler. Here again, in Dill's book they have shown very nice using a lattice model that how one can explain that, and this is a situation. So, this is a polymer of simple 3 bead polymer, 3 bead only, and you see if it is totally elongated, then the orientation has to be in one direction only, and therefore, there is only one way of doing so. If I put all the polymers in a straight manner, all the monomers in a straight manner in a polymer, there is only one possibilities. However, in an intermediate situation, you see how many. So, there here the length is 3, right, here the L is 3, you can see that, here L is 2, you can see that, and here L is 1. Length is measured by how many monomers away it is from the wall. Now, here you see there are 4 possibilities, 4 possible ways to orient them when the length is intermediate. Now, if you want to shrink it, it will again reduce the number of possibilities. So, and that is the reason when you stretch it, and when you release it, your number of W increases, increasing your entropy. Okay. And when it increases entropy, you know that entropy is nothing but dq by t, right. So, it is when the balloon increases entropy, your fingertip will release that heat and it will feel colder. When we stretch the balloon, that time balloon will that time you are working against entropy.
System is spreading in space like
correct.
So, will it not have more microstates?
Okay. So, as a so the question is that if you stretch it, then it should have more microstate, because it is actually kind of an expanding situation. You are thinking of an expansion, right. So, because the kind of a volume or length is increasing. So, the difference is that here when you are increasing a box size, then you are free to move around and orient and make new possibilities. But when you stretch them, every monomer has to align in a particular direction. So, if you calculate the angle between one monomer, the next monomer, the third monomer, they will be like 180 degree, just like what is shown in this particular example. First monomer to second monomer to third monomer, they are linear. Because they are linear, they have only one way of doing it. So, we are not talking about the monomers floating in a box. Here the monomer are connected, and we are talking about only how many configurations the monomer can attain. If you stretch it, there is only one way of making it longer. Take a rope for example. If you take the rope in a straight manner, there is only one configuration that you can get. But if you fold the rope, then there are so many fold. You always fold a rubber in our hand. It will be smaller, but it will have so many possibilities, and that is the reason that it will have more microstates. So, it is not exactly similar as when you expand in a lattice the gas, because in that case the more lattice points will allow the more configurations. Here we are not allowing that configurations, because of the constraints that is present between the monomer itself. So, for this polymer the heat will increase, but the finger will have to lose the heat.
Oh, means you take the heat from the finger.
Yeah, finger will have to lose the heat, and that is the reason. So, when you take a balloon and stretch it, what is going to happen? Entropy will decrease, right. So, if you touch that on your forehead, you will feel hotter, because it is releasing heat.
So, what I was asking is
Take a balloon, stretch it, put it on your forehead, you will feel it is hotter. Why? Because the balloon is releasing heat to your head. Why it is releasing heat? Because its entropy is decreasing.